Today we're going to be going over section 7.3, use similar right triangles. So we're going to start with this theorem 7.5. It says if the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other. So the triangles we're talking about here, so first of all we're drawing from our right angle down to the hypotenuse, the longest side, okay? And then we have three triangles. We have this triangle, we have this little triangle, and then of course we have the original triangle. And what this theorem says is that if you do this, where you draw straight from the right angle to the hypotenuse, you've created these three similar triangles. So how we're going to use that, first of all, example 1, we're just going to identify the similar triangles in this diagram. So I'm going to actually sketch them out too, especially because we're on the iPad, so it's even easier. So this is the first one right here. And our coordinates here, so this is S, this is T, this is S. It's T and that's U. Okay, so that's our first triangle. There's a 90-degree angle here because there's a 90-degree angle there. Our next triangle that's similar is this triangle right here. That with it. So this is R, this is T, and this is U, and our 90-degree angle is right there. And then the last similar triangle is this whole thing. Where this is R, this is S, and this is T. So if we wrote this out, we would say then that triangle SUT is similar to triangle TUR, which is similar to triangle, let's see here, TUR, STR. Notice that these are all our 90-degree angles, so you want to make sure they're corresponding, right? Order still matters here. So that's how we're going to identify the similar triangles. Example 2, we have more of a story problem here. So it says the diagram below shows a cross-section of a swimming pool. What is the maximum depth of the pool? So we want to identify the similar triangles and sketch them first. That's kind of our step 1 here. So, So we have triangle RST. This is our 90-degree angle. This is 152 inches. This is 64 inches, and this is 165 inches. Okay, so that's our original big triangle. All right, and then we have the medium-sized triangle inside of it. Where this is T. Oops, I have this flipped, sorry. Well, I don't have it flipped, that's right. T, M, and R. My M is our 90-degree angle. And then this is 152. We'll call this H. We don't know what this is. And then our last triangle is that little one. That's our 90-degree angle. We have M, S, and T, and this is 64. And this is H. All right, so that's what we know. So step 2, we want to find the value of H. So we need to use the fact that triangle RST is similar to triangle RTM to write a proportion. So I can write a proportion here. Let's start with TM over ST. So I'm using my small triangle, TM over ST. And that corresponds with TR over SR. So then I can substitute in my values. So I have h over 64 equals 152 over 165. So if I do my cross product then, I have 165h equals 64 times 152. And if you multiply that out and then you do your division, you should get that h equals 59. So then our diagram above, you can see that the maximum depth of the pool is h plus 48. Where did that 48 come from? So this right here is my h, right? But then plus the 48 inches, because we're not counting that part. So actually it's this whole depth. So we'd have to do 59 plus 48. So actually the whole depth, the maximum depth of the swimming pool, is 107 inches. So we'd say, whoops. I don't know how to make that go away. Alright. Maximum depth equals, what did I just say? 107 inches. So that's one of the problems here. I don't know why the keyboard's not going away. Alright, the next thing we're going to talk about is geometric means. So you've learned that the geometric mean of two numbers a and b is the positive number x such that a over x equals x over b. When I consider the right triangle ABC, from theorem 7.5, you know that the altitude, CD, forms two smaller triangles so that triangle CBD is similar to triangle ACD, which is similar to triangle ABC. So notice that CD is the longer leg of CBD and the shorter leg of triangle ACD. When you write a proportion comparing the leg lengths of triangle CBD and triangle ACD, you can see that CD is the geometric mean of BD and AD. As you see below, CB and AC are also geometric means of segment lengths in the diagram. So they basically have these rules for how you're going to set up these proportions. So you're going to start with the length of the shorter leg of the first triangle, and then the length of the shorter leg of the second triangle, and then you set it equal to the length of the longer leg of the first triangle over the length of the longer leg of the second triangle, and so on. So then if you see the next one is the hypotenuse and the shorter leg, and then the last one is the hypotenuse and the longer leg. So example 3, we're going to use this. We have our three similar triangles. I'm going to start out by drawing those triangles. I need to make more room for this, sorry. So our first one is triangle RSQ. This is 3, this is Y, this is my 90-degree angle. Then I have another medium-sized triangle. This is SQP. This is my 90-degree angle. I'm just going to line up all of these triangles so they're the same orientation here. And this is QRP. That's the 90. So for our middle one, we don't have any sizes, but for our large one, then we know that this is Y and this is 9. So that's kind of our first step, is to draw those three similar triangles. So now my next step is to write the proportion. So I want to put length of the hypotenuse of triangle RPQ, and then that's going to be on the other side the length of short, I'm not going to put leg, but the short leg of triangle RPQ. Okay, so those go together. And then on my first, so on my left side, this is going to be the length of the hypotenuse again. But now it's going to be of triangle QS. And this will be length of short triangle RQS. Okay, so we make sure we plug those in consistently. So then our proportion will be, let me keep my colors here. Oops, that's not right. So my proportion will be 9 over Y equals, and then it'd be Y over 3. Okay. So now this looks weird because we're going to have a cross product where we have Y show up twice, but that's fine. So what this is going to look like is we're going to have Y squared, because when you multiply two Y's, you have Y squared, equals 27. Now to get rid of a square, you need to take the square root of both sides. So we're going to take the square root of Y squared equals the square root of 27. When we do that, we just drop our square on the Y. And the square root of 27 is not a perfect square. It's okay to put it in your calculator and just get a decimal. Lost my calculator. So the square root of 27 is, 1 second, it's 5.2. The book has you simplify the square roots, so there's still a square, but it's fine. Just use your calculator and get a decimal. Alright, so that's the geometric mean there. So then we have this last theorem, well, two theorems. So theorem 7.6 says, in a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into two segments. The length of the altitude is the geometric mean of the length of the two segments. 7.7 is the geometric mean leg theorem. It says, in a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into two segments. The length of each leg of the right triangle is the geometric mean of the lengths of the hypotenuse and the segment of the hypotenuse that is adjacent to the leg. So they have the proportions there set up for you so you can kind of model how you're doing your problems from these theorems. We'll do one last example together. This is example 4. Find a height using indirect measurement. So to find the cost of installing a rock wall, if you're in your school gymnasium, you need to find the height of the gym wall. You can use a cardboard square to line up the top and bottom of the gym wall. Your friend measures the vertical distance from the ground to your eye and the distance from you to the gym wall. We want to approximate the height of the gym wall. So, how we're going to do this, we're going to set up a geometric mean, and we're going to write a proportion. So our geometric mean, we're going to use, is going to be, let me see here, W, do we have a W? Yeah, we have a W, okay. So our proportion we're going to set up is W over 8.5 equals 8.5 over 5. I didn't color code these ones, but let's just highlight and color code. So W is right there. This 8.5 is right there. Doesn't really show up. And then we have another 8.5, right? That's the same one. And then the 5 right there. So I can hopefully help you model how you're going to set these up. So when you plug this in, you get 5W equals 5 times 8.5, which is 72.25. If you divide that by 5, you get W equals 14.5. Okay, now we're not done. We want the total height of the gym. Remember, W is just this part right here. So we have to add 5 to it. Okay, so the height of the gym then, the height of the gym wall is 14.5 plus 5, which equals 19.5 feet. And that's it. If you have any questions, I have Zoom office hours this week on Tuesday, Wednesday, and Thursday. So please make sure you hop on if you have any questions, okay?